Okay, this video is for AP test review number 8. So this one is a titration problem, and so they're trying to standardize the solution of NaOH. That means they don't know the exact molarity of it, so they're trying to figure out what the exact molarity of the NaOH is. And so they're filling up a burette tube, they're putting the NaOH in there, and they're going to mass out 1.5 grams of potassium hydrogen sulfate, which is going to be used to standardize the base. All right, so anyway, it says, explain the procedure that you would use to make the potassium hydrogen sulfate solution. And they give you the glassware. So a lot of times on the AP test, they want to see if you know how to use the correct glassware. Okay, well, and how to make a solution. So number one, if they give you the option of safety goggles in the equipment list, number one, you should definitely mention that. In the old days of AP, they used to give you a point for mentioning that. Not sure if they would do that this year or not. Okay, I don't know why these numbers doubled up, but they did. But anyway, number two, place a clean beaker on a scale. Now we're going to end up using a volumetric flask at the end to do it, but it's really hard a lot of times to get the stuff that you want in the neck of the volumetric flask when it's in the solid form. So I'd prefer to do it in a beaker. So you put this on a scale and zero it. You measure out 1.50 grams. Then you're going to add some water, but don't add up to 50 because that's what you need to have at the end. So add about 30 and you stir it in the beaker until it's dissolved. And then you're going to transfer it to a volumetric flask. So a volumetric flask is a very good way to make a solution with a specific volume. So a volumetric flask is usually the tool of choice. Okay, so sometimes though, however, they want you to know about like to dispense a liquid. Dispensing, you can use a pipette or a burette tube, but to make a solution of a specific volume, you definitely want to use a volumetric flask. So then you use the rinse water from the beaker after you transfer it, and you want to dilute to the 50 milliliter mark on the flask. Okay, explain the procedure for preparing the burette. Okay, with the burette tube, when you get it, you always want to rinse it out with some water, but then you want to rinse it twice with the solution that you're going to be using in the burette tube. That keeps it cleaned out. A mistake that people make sometimes, like let's say this is the tip of the burette tube, and they rinse it out with water. Well, the bottom of the burette tube keeps water in it, and then when you add the NaOH up at the top, they don't mix up, and basically then you start titrating. Well, the first few drops that you're adding are this water and not the NaOH or whatever you're putting in there. So it's always good to rinse it out twice with whatever you're going to titrate with. All right, here's a classic example of the AP test. They want to see if you can read a burette and do significant digits. So we're going to calculate the molarity of the NaOH. Okay, so anyway, what you can do is, well, so to get a molarity, we need to know two things. To get a molarity, we need to know the number of moles, okay? And it says, so we need to know the moles of NaOH divided by the liters of the NaOH, and we're going to get that from the potassium hydrogen sulfate is going to help us do that. So to get the moles, we're going to start off with the grams of potassium hydrogen sulfate. So KHSO4. Okay, and then we're going to change that to moles. So 1 mole of KHSO4, and that's going to equal 136.17 grams. That's the molar mass. Okay, now we need moles of NaOH, but this is KHSO4. Well, we can get that from the balanced equation. For every 1 mole of this that reacts, you're going to need 1 mole of NaOH. All right, that's what the balanced equation says. So for every 1 mole of potassium hydrogen sulfate that reacts, you're going to need 1 mole of NaOH to neutralize that. All right, and so you do the math there, and we get 0.0110 moles. So we know the moles, so our molarity is 0.0110 moles. Okay, I had 3 significant digits here, so I'm going to keep 3 here. Remember, leading zeros are not counted as significant. Trailing zeros are significant when there's a decimal place in the number. So now I have my moles. Now I got to get how many liters of NaOH was used to neutralize it. So we can get that from the burette tube. Now, you're going to read this volume here. So we know it's like they drain down 25, okay, and then this goes to 30, so that's the 0.5 mark. So 0.5. Now the 0.5 is the mark is shown on the device. The rule is always estimate 1 digit past what's shown. So I'm going to estimate this 1 more digit. So 29.55 milliliters. Okay, that's how much they drained the burette tube down to. Now, where did it start? It didn't start at 0. So we got to figure out where it started. So we got 3.123. So the 0.3 mark is on there. Then we have to estimate 1 more digit because 3.123, the 0.3 is on there. We estimate 1 more digit, and I'm just going to say 5. And so I get 3.35. 3.35. Now we're going to end up subtracting, and we end up getting 26.20 milliliters. Now with adding and subtracting, with significant digits, you always go by the number of decimal places. So this, if you look at the decimals right here, and this decimal is right here, they both go to the 10th, so our answer has to go to the 10th. It's not about counting significant digits. So our answer goes to the 10th. We have to keep that 0 there. So we're going to put that up here. That's in milliliters, so we're going to have to change it to liters. So we would just go in 1 liter, there's 1,000 milliliters. Basically, we're moving the decimal places 2 spots. So 0.02620 liters. That's your volume. So 0.02620 liters. This has 4 significant digits. This has 3. So if we do the math and divide them, we get 0.4198. We're going to show 3 significant digits. So the molarity is going to be 0.420 is what I got, moles per liter. All right, 3 significant digits. Okay, now here's a common problem with the titration. At the conclusion of the titration, the student notices the titrated solution looks more like fruit punch instead of pink lemonade. How would the student's error affect the calculated molarity? Well, a common mistake is a lot of people go beyond the endpoint. They add too much of what's ever in the burette tube, and it goes past the endpoint. And so basically, if you make fruit punch, you're adding too much NaOH. And if you add too much NaOH, okay, your milliliters would be greater, which would make your liters greater. And so if in the molarity calculation that we just did, in the moles divided by the liters, if you're adding too much, okay, it's going to make the liters greater than it should have been, and that's going to make your molarity smaller. Okay, that's how that would affect that. All right, in another experiment, the student uses a drop counter and creates this curve right here. It's a titration curve. So this one they're doing potassium hydroxide and nitrous acid. All right, and so place an X at the equivalence point. So remember, the equivalence point is the inflection point where the curve changes direction, but it'd be about right in here somewhere. Okay. Okay, calculate the molarity of the HNO. Okay, so you can use the, I don't know what we call this, a titration equation, but molarity acid, volume acid over Na equals molarity base, volume base over Nb. Now, the N's, okay, are the coefficients right here. So what number is in front of there? 1. What number is in front of here? 1. Okay, so it's a 1 to 1. So anyway, we can just put in, okay, calculate the molarity. So MA, we don't know that, times the volume of A. Well, we got to read up here, and it looks like they're putting 100 milliliters in. So 100.0 milliliters. Okay, divided by Na, which is 1, equals molarity base, which we got to look up here, and it's 0.100 molar, times the volume of the base. So now the volume of the base is the volume at the equivalence point, and so that's 20.0 milliliters, divided by the N, so that's that number right there. And if we would happen to do all the math, we get 0.0200 molar is the answer that I got when I push the buttons. Okay? Okay, now, letter C. So this one says, draw a particle diagram showing the species in their proper orientation to each other at the 20 milliliter mark. Okay, well, I don't know if I worded this question great, but basically what I wanted you to show is the ions dissolved in water and their orientation and the approximate number. Now, anyway, here's the thing. At the equivalence point, which we marked right here, at the 20 milliliter mark, that's at the equivalence point. Okay, at the equivalence point, exactly 1 mole of this has reacted with 1 mole of this. All right, and so when 1 mole of this reacts with 1 mole of this, all of it changes into this and this. And you can see for every 1 K, you have 1 NO2. So what I was looking for is that you could have 1 potassium ion for every nitrite ion. Okay, you wouldn't want to have more potassiums than more nitrates. Like you could have 2 and 2, 3 and 3, 4 and 4. But the main thing is that the potassium ions and the nitrate ions or nitrite ions have to be in the same proportion. Okay, also surrounding it, positive ions are surrounded by the negative end of water, which is the oxygen end. The negative ions are surrounded by the positive end of water, which is the hydrogen end. Okay, another thing to keep in mind is the size of the ions. I've seen on AP tests before where if you don't draw the ions to the relative size, you could get that wrong. And so the potassium ion, I'm assuming, is smaller than the nitrite ion because it's got 2 oxygens and a nitrogen on it. So I tried to draw them a little different size. Okay. Okay, now if you were asked to draw, this is the last question, these again with potassium and nitrite, but at the 25 mark, so the 25 mark is right here. And so here's what happens if you remember when you make a titration curve, you keep on going. And so what they're doing is they're adding extra KOH. Now, what's going to happen is there's not going to be enough HNO2 to react with that extra, okay? So anyway, there's going to be extra KOH in there. So what you should do to finish this off is you should add additional K and OH ions in the solution. Add extra ones. Okay, I don't know, there's not really a set number that you'd have to add, but you would have to have extra K and OHs in the solution. Okay, there would still be like for every 1K you would need an NO2, but then you're going to have extra Ks and extra OHs. Okay, that's it for that video.